All right, our final speaker is Professor Christian Frankenberg. He's a professor here at Caltech. And he was, before he was at Caltech, he was a JPL, fully JPL scientist. And so I've known Christian for a while through JPL. And we kind of started around the same time and following kind of parallel tracks that eventually converged when fluorescence kind of blew up in front of us. And Christian was working on some of the retrievals for CO2, atmospheric CO2 from GOSAT, and knocked on my office door one time and said, Josh, we also get this other thing called fluorescence from GOSAT. And I remember taking a biology class in high school or university or something like that, and they mentioned it. Is this interesting? And we kind of put our heads together and thought, well, this is really interesting. This is something that in the ecological community, we have always wanted to know what's happening to the plants, but we can either see if they're green or they're not green. And it's kind of like if your doctor, you want your doctor to tell you if you're sick, before you are no longer visible, for better or for worse. So Christian and I started looking at fluorescence and kicking it off. We produced that GRL paper in parallel with Joanna Joyner, who was also working on it out of Goddard. And so we looked at it as this new insight into a global understanding of what's going on with photosynthesis in GPP. And then Christian put together a fluorescence workshop here at Keck and Caltech, of which, how many years ago was that? Wow. Okay. Yeah. Wow. I feel like it was just yesterday still. So yeah. Hopefully we have made some progress since then, and I think Christian will tell us a little bit about that.
Thanks, Josh. So first of all, sorry for not having been here earlier this morning. I had to sit in a qualifying exam, and I hope that I'm not overlapping too much. I know what Joe roughly talked about, so I'll try to go over some of that stuff a little bit more quickly than I anticipate, but just as a kind of little recap, this is one of the figures that we created as the end result for our report from the last KISS workshop 5 years ago, as we now just learned. And this is an interesting part because it kind of shows us all the different scales that we are actually looking at, from the chloroplast level actually to the leaf scale, to like a single tree, to the landscape scale, and then to what we actually see from the satellite, which is some of those aspects I'll actually walk you through in this talk. But maybe going back to the origin of everything is basically the absorption of sunlight drives it all. Without sunlight, there would be no GPP. Without GPP, there would be basically no other life on Earth, because it's the energy input of everything. And if we look at the absorption by chlorophyll, so what we typically call PAR, it's always, as you know, between the 400 and 700 nanometer wavelength range, is where the chlorophyll and the whole antenna system, also carotenoids, absorb light and actually funnel it to the reaction centers. And in terms of how much of that is used and what is the resulting photosynthesis, they're actually the biggest two factors is A, how much light is absorbed by the antenna system. So it's not the total absorbed light, but how much light is actually being absorbed by parts that can do photosynthesis. And then once it's absorbed, how efficiently is this light being used for photosynthesis? In principle, if we can tackle these two questions, we should be able to resolve what the resulting photosynthesis is. So what is happening once chlorophyll or carotenoids actually absorb light? It's basically funneled to the reaction center. And then if you have like absorbed blue light, higher energy light, there's an energy conversion to the lowest excited state. So actually light that is below 650 nanometers rapidly decays to a lower excited state at around 650, 680 nanometers. And then from this can happen within picoseconds. And then from this state, this is actually semi-stable, stable to within like 6 nanoseconds. And this one, then from there, we can get the fluorescent signal. If this decays, falls back to the ground state, it actually fluoresces light, in this case, in the 650 to 800 nanometer range. But there are different pathways how we can quench this lowest excited state. One of them is doing photosynthesis, and the others we will learn about will be, and Joe talked about this, is non-photochemical quenching. And this step here, for those of you who are always confused about the PAR units being micromole per square meter per second and not watts per square meter, this is the reason why it is micromole. So we only count photons basically because For the plants, it doesn't matter whether you have a 400 nanometer photon or a 700 nanometer photon, they have the same energy, because you basically lose that energy in the beginning step here. So it doesn't matter what wavelength you absorb it, it kind of drives the same physiology. So once we have the unstable higher state, this is the very fast transition to the lower state. We are actually interested in what is happening to this lowest excited state. And this is somewhat stable lifetime of a few nanoseconds. And once we are there, it can actually do several things. One is re-emitting a photon, which is basically the fluorescence that we see, which on this display is slightly shifted from the absorption. So we have these fluorescence emission spectrum basically in the 650 to 800 nanometer range. It can also fall back to the ground level, release heat. It can transfer energy to another chlorophyll. And it can perform photochemistry, which is actually what it's supposed to be doing. And in fact, if we talk about the best metrics for the yields, it is actually, if you can measure the lifetime of that state, this is actually the most accurate metric for the different yields, for the fluorescence yield, because the lifetime is determining how many other quenching mechanisms there are apart from the natural lifetime of this excited state, which is on the order, if you look at the kind of isolated chlorophyll in a solution, they actually have the highest fluorescence yield because they have no other quenching mechanisms. So there the lifetime is actually highest. But if it's embedded in a photosystem in plants, the lifetime is actually much shorter because you have other mechanisms of where this energy can be going into. But of course, plants are not only light limited, so they not only always take the same, so they work at different yields under different conditions. And one example here, which is a nice one from the Fun Camera book, is actually light response curves for two different leaves, one that grew up in the sun and one that is actually more acclimated to shaded conditions. And of course, plants try to maximize their output and also minimize their investment into resources. So plants that actually grew up in the shade, they are not used to high light conditions, so they don't really have to work with high light conditions as are seen here. So their typical light response curves levels off a lot faster than plants' leaves that actually grew up in the shade, like at the top of the canopy. And we can also see that we are first often in the light limited regime, but once we go to higher irradiances, we actually level off, and to some degree the photosynthetic efficiency actually goes down with increasing power levels in this case. And this is true for a leaf. For a canopy, it will be more complex because a canopy is then the kind of a summation over all kinds of leaves that work under different power areas. So you will have shaded leaves, you will have sunlit leaves, you will have all kinds of different power levels within the canopy that you have to integrate over, which complicates this thing and probably linearizes it to some degree. But now, this is just an indication that the light use efficiency is really important, and how they can actually generate the part of how much photosynthesis they can still do under high light conditions is basically an investment in Rubisco, which is basically reflected in the VC max parameters. But this comes at a price because there's lots of nitrogen needed to actually generate Rubisco at these sufficiently high concentrations, and the maintenance respiration is higher if you have higher VC max. So at low light levels, these plants that actually grew up in the shade are actually doing worse than the ones that these are doing worse than the ones that grew up in the shade at the low light conditions. So light absorption can be dangerous. So if the plants are actually absorbing too much light, more than they can handle, they have to funnel that energy, because otherwise you can get toxic photoproducts that actually damage the plants itself. So you get triplet states of chlorophyll, superoxide, singlet oxygen, hydrogen peroxide. These are all very oxidative species that can damage mostly the D1 protein of PS2 and eventually lead to kind of photoinhibition. And I thought of this as a kind of, so you have this assembly line, and once you put in too much light energy, then the dark reactions can actually handle. You'll get something like this, where you have the assembly line of light coming in. And then if you can't stop it or move these elsewhere, you actually get a big mess, and the plants can get really terribly hurt. So what pathways can we do to actually avoid this kind of situation? Oops. Here. So the way we are doing it is there's not only one outlet that you can go to, but there are several assembly lines that all work at different speeds. So we basically, if you look at the light absorbed by the chloroplasts here, and they can move around or ultimately be funneled to the reaction center here. They can undergo different fates. One is photochemistry, of course. Then there's radiative decay, non-radiative decay through heat. This is an important one that Joe already talked about, non-photochemical quenching. So this is basically a control knob with which they can quench the energy that would otherwise get very dangerous to the plants. And then there's always fluorescence also coming out. And the yield of one specific term, in this case we only write it for fluorescence, would be the rate constant of fluorescence, which is assumed to be constant in our case, divided by the sum of the rate constants of all the other processes, which would be photochemistry, non-photochemical quenching, and then the non-radiative decay. So which ones can we control? Kf and Kd is supposed to be constant. Kn and Kp can change dramatically. In fact, if we look at pure chlorophyll solution, where Kp and Kn would be 0, you would get a fluorescence yield of almost 1. So this is why a pure chlorophyll solution would actually fluoresce much higher than the chlorophyll in plants. So this is just an example where you illuminate a tube with chlorophyll and you can see it basically moving out here. And this is something that was already found in 1874 by Müller. But then there's different things. So one way of doing it is actually absorbing energy. Sorry about that. Absorbing energy and funneling it away through different mechanisms after it's being absorbed. And that, as I will talk about it a little bit later, will lead to some complicated aspects of the fluorescence yield versus photosynthesis yield relationship. But there is, as Joe mentioned, a more direct thing which leads to a more direct correlation between fluorescence and GPP, which is trying to avoid absorbing sunlight in the first place. One example here is this nice little leaf under normal conditions, so 0-degree leaf angle index, illuminated with a very low PAR level of 4 micromole. Has this leaf position, and then we give it a sun fleck. Sun fleck, for those of you who don't know, it's basically in a canopy when you get a sudden burst of light. So sometimes you get the sun basically down to the bottom of the canopy to the understory, so you get a rapid change in illumination. So if you get this one around 1600 micromole, which is a pretty decent PAR level, they can probably immediately change their leaf angle positions, basically trying to minimize the absorption of light. And then once you turn this off again, the leaves basically reorient itself to actually absorb that light here efficiently. But they try to avoid absorption in the first place once you hit it with very high light conditions.
They can do that in 25 minutes?
They can, yeah. Actually, soy does that too. Some plants do the opposite, so they try to orient itself perpendicular to the incoming light to actually maximize light absorption. It depends on whether they are light limited or not. Like, this is really depending on the plants.
But the time scales are relatively fast.
The time scales are relatively fast. Yeah. And there's also time scales associated with non-photochemical quenching, where one is acting faster than the other one. So the relaxation is actually taking a little longer. There's interesting papers studying how to speed that up to actually maximize the efficiency over this integration here. But this would result more or less in a one-to-one correspondence in a change in SIF and GPP, because you basically change APAR to the same degree. The other method is chloroplast movement. So even if you don't move the whole leaf, like if you have the leaf chambers, we kind of force the leaf in there anyhow, so we can't really move its orientation. But even if you fix the leaf, the chloroplasts can actually move to the cell boundaries here and thereby minimize absorption, because they are stacked on top of each other and thereby would absorb less light in this case. This is actually triggered by blue light. So these are chloroplasts here in a leaf, in the darkness, weak blue light and strong blue light. So these can reorient themselves and thereby also change the amount of total absorption. And I see my timer is not running, so I have infinite time.
I'll let you know.
Okay.
That's my fault.
Good. But I don't know how clear it was when Joe talked about it, but I think it would be good to repeat this part again a little bit. There's often some confusion about PAM, which is the pulse amplitude modulation fluorescence, and what we measure from space. And I think I just want to spend a little bit of time to really explain the differences. What PAM is measuring and what we are measuring, these are two different things. Who worked with PAM before? Someone did PAM measurements? Joe, the only one, Oli, of course. Okay, so what PAM is doing, so you can think about your Lycor system or Waddell system that does the leaf level gas exchange measurements. And when you have a PAM system, you basically have an active source of light, and you measure the response in fluorescence. But you don't measure the response in fluorescence from the total incoming PAR. You only measure the response of a modulating signal. So if you have, let's say you take a light response curve in a PAM system, this would be the light, actinic light. This would basically be PAR. The LEDs are off, so you have 0 light. You turn it on. You do a flash or a very high light condition, like maximum PAR. You basically darken it a little bit, and you turn it off. In theory, when we do fluorescence measurements from space, this would give us a much higher signal than this one, even if the yields are the same for the fluorescence yield. Even if always 1% of the light goes into fluorescence, this and this would be basically by the same factor, it would go up. What PAM does, though, is it doesn't measure the response to this signal. It measures the response to an AC modulation. So on top of the PAR level that you have a tiny modulated signal that actually goes on, off, on, off, on, off. And you just measure the response of the fluorescence that's being re-emitted from the leaf due to that modulation. So you basically take that different signal between on and off, and this is your FS basically in PAM fluorescence. But bear in mind that this is always related to a constant PAR. No matter what the background is doing, you only measure the modulation here. So if you then measure the total light that would illuminate the leaf, it would go like this little modulation around 0, and then you step up the background light, but you still have the same modulation. You step up the background light, but you still have the same modulation. And what you measure then in the total signal in fluorescence coming out would be something like this. You have this AC signal. The DC goes up. The AC signal actually gets a little higher. The DC goes up. The AC signal goes higher. And then you can decompose this part in the PAM fluorescence. That gives you a direct fluorescence yield. It's not the total fluorescence. It's a fluorescence yield. And this is very important to bear in mind. So the decomposed AC signal that you get through these is basically almost a derivative of fluorescence to PAR changes. Whereas the actinic signal, basically this baseline here, would be more akin to fluorescence. So if you were to multiply the yield times APAR, you roughly get something like this in this equation here, with the caveat that we don't always know APAR perfectly. So it's actually, in some cases, it's pretty hard to actually convert the FS that we measure from PAM into total fluorescence. But each and every FS signal in PAM is a yield. It's not a total flux. It's always a yield, which makes it so powerful because we need yields to actually use it. And this is the case here. If we were to actually analyze all of these different fluxes, so we want to get the photosynthetic efficiency and fluorescence efficiency and non-photochemical numbers out, we need yields because we can't work with the changes in APAR. We need something normalized. And now we can walk through that plot here a little bit more if we do a light response curve. So this would be a case where we have just a modulating light beam on. So this is a dark leaf, 0 actinic flux. Then you turn on the actinic light. The fluorescence goes up, not the absolute fluorescence. So this response is not due to the actinic light. This response is the yields are changing because you have background light suddenly. I'll walk you through that a little bit more. And then you get this Kautsky phenomenon here that the fluorescence yield actually then, once it's illuminated with actinic light, rebalances all of the different parameters here until it reaches kind of a semi-steady state at the end. And we can turn that light off again, and then it drops suddenly even below this level that it would have in the dark. But if a leaf is in the dark means all these quenching mechanisms that go into Kn are completely relaxed. So Kn is supposed to be 0. In this case, if it is in the dark for like half an hour, some people take the whole night. And the Kp value is maximum in the dark adapted leaf. That means that the fluorescence value is actually relatively low because Kp is really high even though Kn is 0. If we then turn on a saturation flash, so what a saturation flash is doing, it's hitting it with like 8,000 micromoles, something that the plants can't really be using. And that is closing all the photocenters. So that's basically turning off Kp. The saturation flash in PAM is shutting down Kp. So what it does basically, in this case, in the dark adapted leaf, it shuts down Kp and Kn is still 0. It can't react that fast. This is only like a fraction of a second that you turn it on. And then once you go off that saturation flash, but then look just at the actinic light, during that curve here, Kp is somewhere between 0 and the maximum Kp. It's actually changing during that time period. And then suddenly, now the Kn is changing. The Kn is increasing during that Kautsky curve. Because now the plants see actinic light, so they start turning on this Kn knob and slowly increasing it until we reach a steady state of all the yields in the end. If we do a saturation flash again now, so we see that suddenly the yield due to that flash is not reaching the maximum anymore, like it did here. But the only difference between this value and this value here is that Kn changed from here to there. So by using that difference, as I will show later, we can actually derive directly how much energy is going into Kn and how much energy is going into Kp. And this is the power of active fluorometry. So if you look at this so-called Fv over Fm signal, this part that is lost from the dark adapted leaf to the light adapted leaf, this is exactly non-photochemical quenching. And it only works because we are working with yields, not with absolute numbers here. This part here, that is basically being lost, that changes from the saturation pulse due to the and the steady state, this is exactly the PS2 yield, basically. And this is like Bernard Gentil's paper, who actually was in the workshop 5 years ago, is probably one of the most heavily cited publications in our field with more than 5,000 citations. Because this is at the heart of the PAM measurements, that you can actually get the PS2 yields from these measurements of PAM. And then you can get the maximum PS2 yield, which is basically this part here in the dark adapted leaf. That's typically around 0.82 or something. Joe, is that right? And then what we measure from space, though, is just this FT signal here, but not really this FT signal, because this is a yield. We would have to multiply FT with APAR. And this is kind of the signal that we measure from space. And now the complication is how can we relate this part here to the nice things that we can get from the PAM modulated fluorescence. Ideally, we would like to flash our plants all the time so that we can kind of give it a saturation pulse, but that would be a pretty powerful laser that we probably have to fly in space. So this is something we can't really do. So what we have to work with is basically just a steady state fluorescence, which is this FT value times the APAR value. And probably most of what we see from space is APAR due to chlorophyll. The ones that's driven by really changes in the yield are probably a lot smaller impact factors than changes in APAR. But this would be the holy grail to really try to fully disentangle them, which is not always very easy because these changes are much smaller, which is shown here by Albert Porcar-Castell's review paper, where if we plot the quantum yield of photochemistry against the quantum yield of fluorescence, we get this typical behavior where we have an anti-correlation of the yields at low light. So if Kn is not yet turned on, there's actually an anti-correlation, because then if you look at the equation, Kf and Kp are fighting against each other. So if Kp goes up, the fluorescence yield has to go down. So they basically share the same resources, and thereby they anti-correlate. Once Kn kicks in, you have like your enemy is my enemy. You basically have another factor that competes for these resources and basically shuts down both of the yields a little bit. And this is probably in most cases what we observe from space. We are more on this curve where the yields are correlated. But they are not, the slope is not perfectly one-to-one. So if you get a 50% reduction in the PS2 yield, we don't always get a 50% reduction in the fluorescence yield. It's slightly shallower. So that makes this relationship a little bit more complicated, and to some degree causes some of our heads to scratch why we don't really see that from space. But we also don't have the time resolution quite often. Ooh, now I see it ticking. So I'll skip through this really quick. The other complication is, I should mention that in principle the fluorescence signal that we see is a superposition of fluorescence emanating from the photosystem 2 and fluorescence emanating from photosystem 1. Where everything I said so far, we have to be careful, because what we said, we always say PS2 yield, which is because only in PS2 is the Kp really variable. Because there's back transfer of excitation at 2 high electron transport rates, and the assumption is that for PS1, Kp is constant because you have a steeper redox gradient in the electron transport chain, and the P700 plus itself is a quencher. And we have variable Kn working in the antenna system here, where we can quench Kn And for PS1, the basic assumption is that Kn is also constant, whereas this might not be really too clear. Why does it matter? It matters slightly because there's different spectral contributions from PS2 and PS1, depending on what you look at. So it's supposedly the 680 nanometer contribution of PS1 is rather negligible. So you should see a stronger impact of Kp on the wavelengths shorter than 700 nanometers than longer than 700 nanometers. And towards disentangling these goals, we actually worked on a modified gas exchange system where we can do PEM spectrometry, this PEM fluorometry, and basically the passive SIF measurements in a spectrally resolved sense at the same time. So we are working on a second paper that actually looks at how we can use the shape to disentangle Kp directly, which seems promising, but it will be tricky in the real world. And now I have to be really fast. So remote sensing of vegetation and SIF, as I said before, this is basically the chlorophyll absorbency in this part, and this is the fluorescence re-emission of light in this area here. The complicated part in most of what I said before with the fluorescence shape is that this lower peak here at 680 nanometers is, of course, overlapped with chlorophyll absorbance. So you basically can reabsorb fluorescence in this first wavelength peak here that's being emitted. That can be reabsorbed within the canopy. And if you look at typical vegetation measurements that Joe also talked about, we often make use of this so-called red edge, where the plants are reflecting way more light in this 750, 730 nanometers and above wavelength range, because they are highly reflective, but they are, of course, absorbing most of the light in the 400 to 700 nanometer range. And by using wavelength reflectance ratios here, we can actually derive the NDVI index. But if we were to take pictures in this spectral range, which is not visible to the human eye, we get something like this. And a shout out to the KISS director, who actually, it's one of his hobbies to do near-infrared photography. And if you find his website and his private ones, this is actually the Olive Walk at Caltech. There's lots of other interesting pictures using near-infrared photography where you just change the bandpass, the filter on your camera. So this is basically light at 700 nanometers and above. So this is how the world would look like. Very little stray light from the sky, but you see the green leaves are really the brightest one in the sky. So they're kind of as bright as snow usually in the visible spectral range. But you can browse through these pictures, and this would probably go back right to your NIRV. So this is the near reflectance almost that we would be multiplying the signal with again. Really pretty photography usually. So how do we measure an additive signal? This goes back to Josef von Fraunhofer that actually detected these so-called Fraunhofer lines in the sun's photosphere, where we see that the sun is not a perfect blackbody emitter, but there's certain spectral ranges that are basically blocked out or rather dark. And the basic idea is really simple. We have wavelengths and intensity, and imagine we had a perfectly black line where we have no emission coming, no light coming through. We would have a signal here that is high. It would drop in a specific wavelength area to 0 and then go up again. If you have something like an additive signal that is kind of just adding a baseline to that whole thing, we would just shift the whole thing up. So we suddenly have this one not going down to 0 anymore, but everything is shifted up. And this basically changes the I inside divided by I outside ratio. And this is being used for the fluorescence retrieval. If you had a perfectly black line here, you could just measure the radiance in this curve here and directly get fluorescence, so that would be rather trivial. In most cases, the transmission here is kind of 80%, 70% of what we typically see. So you need to do some math to get it out, but it's actually not much more complicated than that. This is actually what people already found in 15.6, where they looked at lunar luminescence. They actually used Fraunhofer lines looking at the moon, basically reflected sunlight from the moon, to actually state that they detected luminescence features on the moon's surface. And this is almost the same picture that I showed before, just published, as you can see from the font and everything, a little bit earlier. Called this particular one is not from the earliest studies, but you see the principle here is the same. This ratio, that's infilling ratio, changes if you have an additive offset to the overall signal. But in this part, they actually assumed some thermal signals that actually have a relatively high temperature that might cause these additive signals. Later on, there was another, this is just a nice overview paper in '84 that actually looks at the lunar luminescence and the filling in of Fraunhofer lines in moonlight. in a little more detail, saying that a lot of this might be due to inelastic scattering. But the more interesting part probably comes from this landmark paper by Granger Ring from 1962 that looked at anomalous Fraunhofer line profiles, basically comparing spectra of directly reflected sunlight from the moon versus looking at slightly off the moon, basically where you only look at scattered stray light from the Earth atmosphere. And they found that the Fraunhofer lines are basically distorted. So their shape changed and the depth changed if you look directly at the moon versus the stray light. At that time, it was really not yet fully clear why that would be the case. It's coming more from the atmospheric community. But then we had Brinkman actually coming from our division here at Caltech in '68, explaining this theoretically using rotational Raman scattering. So basically, the typical Rayleigh scattering by nitrogen and oxygen in the atmosphere, a small fraction of that is not elastic but inelastic. So it basically reshuffles wavelength. And this can cause an infilling of these so-called Fraunhofer lines. And they actually also distort the shape a little bit. And this is one of the earliest papers discovering this one. And the next one is basically by Waddell in 1980 to really model it in a more quantitative sense, also depending on different viewing geometries, later going into polarization regimes as well. But the funny thing is that all of these papers here, the ring effect, so-called ring effect, which comes from Granger Ring, is actually instrumental in doing trace gas retrievals in the UV vis. So most of this ring effect actually has a bigger structure than all the NO2 absorptions or SO2 absorptions that we typically see in UV vis spectroscopy. So the fact that we have to work with Fraunhofer lines in the atmospheric community has been there all the time because they are a pretty big disturber. So it probably doesn't come really as a surprise that Joanna and me, from more the atmospheric side of things, we're looking first into the Fraunhofer lines compared to the people who worked on the ground, on plans itself. This is just like a little historical background. And maybe I will not be able to walk through all of these here, but I think most of the people are actually in the workshop, so I can maybe show some of the remaining slides if the time runs out later. So how do we do this? So this would be basically a disk-integrated solar irradiance spectrum at like 0.05 nanometer spectral resolution. We would not see like one Fraunhofer lines, but we would see hundreds over that whole spectral range, covering like 650 to 800 here. So this is the typical range where fluorescence is being emitted. If we go down to the top of the canopy, this would be roughly like what we would see as an irradiance, basically the shortwave incoming radiation, where we now have the Fraunhofer lines, but then we have added water absorption features and the oxygen absorption, the O2A band here, which is the one that we cover with OCO2 and GOSAT. And then we have the O2B band here, C band over there, and strong water absorptions nearby. If we then multiply this and look at a resulting reflected radiance that we would see if we were to look down on the canopy, we would see a shape like this, where this basically the umbrella here is roughly the solar irradiance times the typical reflectance shape of of plants. And then we would overlay something like a fluorescence spectrum here. This is times 50. So if you look at this range here, the fluorescence here only adds about 1% of radiance to that level. So this is the difficulty why we can't really look at it directly, because it only changes the reflected radiance by roughly 1%. In this range, by a much higher percentage here, because it's basically re-emitting in a range where the plants are rather dark. So what's the overall impact if you have like a pure reflected radiance like this one, and one if we have this fluorescence signal added to it? It would look like this. This would be a ratio spectrum if you would build a perfect canopy that would not fluoresce, and one that would fluoresce. In the ratio spectrum, we should see something like this. So basically, these bumps here we should ignore because these are really hard to disentangle from any other weather variation. But we see the infilling of these deep lines. So these would be the strongest infilling if you look directly above the canopy, is basically in the oxygen absorption features because they are so dark.
So those are with?
Sorry?
Those are with SIF, the orange one?
Oh, this is, no, this is, okay, with SIF divided by without SIF. And this is just separated by just looking at the all absorptions, and the blue one would be just looking at the Fraunhofer lines. And this is the main reason why people on the ground are mostly using the oxygen bands. Because in the oxygen bands, if you look at the ground, these are much stronger features and much easier to measure. You don't need the high resolution spectrometers. you can just look basically at a reference target right near the canopy, and then you basically move it over the plant and measure that one as a baseline. So it's much easier instrumentally.
The orange lines include the oxygen.
Yeah, exactly.
The smooth feature, that's
The smooth one, let me take that smooth one out because we can't really measure that one perfectly. So this would be, if I take the smooth one out, the infilling would be roughly looking like this. Oxygen would go off the chart here. That's why I cut it off. But then we see that all these Fraunhofer line features, you see now the infilling is around like 1%. So you would at least need a spectrometer that works at that resolution and has better than 100 signal-to-noise ratio to actually use these, to invert these. And typically we need measurements at 500 to 1,000 SNR to really pick out this weed from what's actually going on. The main complication for the oxygen bands arise, so this only works under the assumption that the oxygen column doesn't really change. But especially if we have scattered sunlight coming in, then suddenly the oxygen lines will change depending on the amount of scattered light hitting the canopy. So it's not a time constant. The Fraunhofer lines are kind of always inert, so they don't really change in the atmosphere. The oxygen lines, the depth of the oxygen lines in the incoming radiation depends on the photon path length distribution, which is hitting the canopy. So if you have a cloud somewhere, that might change your radiation field. Then you will see more or less oxygen in there. So all these things are a lot more complicated if you use the oxygen band here, or if you have like deep canopies where you might have multiple scattering within the canopy and you basically see oxygen along that light path all the time. So it would be embedded in here. But this is basically the main problem. There's a couple of nice lines here. This is the so-called H-alpha line, which is around 656 nanometers, which is a very strong Fraunhofer line that we are actually looking at now using ground-based spectrometers. But if you look at these green features here, if you can see them, it's really faint. This is all we are working with right now. So these two things here are the micro windows for OCO2. That's all we use for the retrieving fluorescence. Basically, it's two Fraunhofer lines here and one on the other side. The GOM2 works more or less with the whole spectral range here, so that's why you have to use somewhat more statistical tools to get that one out. But it's also mostly sensitive to the integrated effect of all the Fraunhofer lines in that larger spectral range. So this is basically how we do it from space. I'll skip the earliest work with GOSAT. Probably seen this. Just want to go briefly into what we can do right now. And this is a paper that Ying led on OCO2, basically. Just looking at the main advantages of OCO2, but maybe also at the main disadvantage of OCO2. With OCO2, we can get really fluorescence values at a unique spatial resolution. So if you look at this plot here, Chicago beforehand, with GOM2, we basically would see like humongous 40 by 60 kilometer ground pixels. So we really never have a homogeneous pixel within there. And with GOSAT, we basically get a spot here, spots there, but we lose basically the spatial patterns within there. But if we zoom in here with OCO2, suddenly we have a nadir track that's only like 10 kilometers wide, but we have 8 across-track footprints, and each footprint is around 2.3 times 1.3 kilometers. So we actually can see small-scale variations in OCO2 data, but usually only along the orbital track. So once we go across track, we're actually losing a lot of coverage, because OCO2 does not cover the entire Earth. It only covers around 5% of the Earth's surface, maybe. But along the tracks that we actually have, we have pretty good coverage. And we can even zoom in here and see what happens if we fly into Chicago in this case, which is kind of unsurprising that we get a lot less fluorescence in the urban areas here. But this is mostly an example of what the spatial resolution of OCO2 could provide. And how does it look with time, Michelle? Is it a hard cutoff due to the...
We've got 2 minutes before the group riots for lunch.
Oh, okay. Let me just, because we can talk about some of these GPP modes and everything later on. One interesting thing is that we now build an imaging spectrometer for airborne observations, where we can now go to something on the order of 10 by 10 meters if we fly that airplane over the ground. But now we are suddenly not, this would be a real OCO2 spectrum, and this is a real spectrum that we now take with a CFIS instrument. So we are not restricted to these two Fraunhofer lines anymore now here, but we measure all of these Fraunhofer lines in this range. And this really boils down the single measurement noise that we get with a CFIS instrument. Much more accurate measurements of fluorescence, because we cover way more lines than we did before, and we go into a range where the fluorescence signal is actually also a little bit higher. That makes it easier. And we were able to use this instrument already to do OCO2 validation. So if you have 2 orbit tracks here from OCO2, we actually try to underfly it. You see these wiggly white lines here. This would be the swath of the airborne instrument. We were underflying OCO2 at that time. And then we can directly compare the fluorescence data from 2 of these tracks. And the red one here is CFIS, and the black one is OCO2. So we have a nice gradient for some of these flights where we have a pretty good correlation between the measurements from the airborne instrument and the satellite measurements, which is probably the first ever real validation of a satellite instrument for fluorescence, which is otherwise slightly harder. And just 2 last slides, because I want to give a shout out to KISS. We were able to finance like ground-based spectrometers that can also use the Fraunhofer lines, that don't only have to use the oxygen lines from the ground. This is one example where we installed the instrument at Nivod Ridge at the Flux Tower site in Colorado. And first time I chickened out somewhere here. At the end, I was at the top, but I always had to hold like one hand, so somewhere on the structure here, so I wasn't really very useful. So luckily, 2 more daring people installed the instrument up there. And the other one is just if you want to watch corn grow and soy grow. These are 2 sites. So you see now here we can actually point the spectrometer into different directions using an azimuth scanner here. Inside is an elevation scanner. So we can look at the 3D distribution of fluorescence emanating from these canopies. And you see the corn grows like crazy. The soy lags a little bit behind. But this is a full seasonal cycle that we have now. These are basically being disassembled as we speak, probably, these instruments. But this will be kind of one of our first studies where we can now look at the full diurnal cycle of fluorescence during a whole growing season in 2 different crop areas here, a C4 and a C3 domain. And if you look really nicely, sometimes in the soy you see these diurnal patterns in the leaf movements. The soy actually orients the leaves towards the sun, I think. So you can sometimes you have the feeling that you get this little clockwise movement in there, but this is only hourly data here. But this is basically where we stand right now, and where we will be able to get a much better idea of the change. And because on a diurnal timescale, it's easier to look at changes in the yield versus changes in APAR. But on the timescales that we do with the satellite, it's really, really hard, because within a week, also repeat time that we have, everything changes. So probably APAR changes by a lot once we measure the next time with the satellite. But we know that from the morning to the evening, the APAR doesn't really change that much. Say FPAR. Thanks.